morning, welcome to new lecture. Today I will look at today's slope deflection method. In order to solve indeterminate structure, generally there are two methods. One of them it is force method. We call it force method or superposition. Another method it is displacement method. Displacement method will be divided to the three methods. Depending on the problem nature, we will use three different methods, and all those three methods we call it displacement method. Later on you will see why we call it displacement method, because we find relationship between internal force and displacement. That displacement can be lateral deflection or rotation in the node, and then we will satisfy equilibrium equation, because our unknown first, they are in terms of displacement. For that reason we call it displacement method. Displacement method will be divided to three different methods. One of them it is slope deflection. Method, very unknown method in order to solve indeterminate structure. Another one it is moment distribution method. Another one it is direct stiffness method. We will look at all these methods one by one. Another name for moment distribution method, in some book you will see, they call it Hardy-Cross method. Hardy-Cross, it is the name of guy, he developed this method. Later on I will explain in details. But first today we will look at this method. It is displacement method. Among displacement method I will explain slope deflection method. Let's see what is this slope deflection method. If we have one indeterminate structure, we can divide that indeterminate structure to several members. For example, we have this structure. We can look at today A, B, C, D, E, F. We can look at two different members and write a slope deflection equation for different members. And I will explain that slope deflection equation, how we can end up with that slope deflection equation, which is very easy. But first we should look at two independent degree of freedom to see how this structure will deform. For example, if we look at today one simple structure like this beam, if I apply load here, displacement or deformation of this beam will be something like this. So only I will have one deformation, and that is rotation at point B, that is theta B. If I look at the simply supported beam, subjected to, for example, point load, how it will deform? It will deform something like this. How many independent deformation I have here? Two independent deformation, A, B. One of them it is rotation at point A, we call it theta A. Another rotation at point B, it is theta B. Or if I look at this frame, in this frame I have A, B, C, D. I have 4 joints. Each joint can rotate, but joint A and D, because we attach to the fixed support, they cannot rotate. Rotation is 0. But joint B can rotate, joint C can rotate. For example, they form, depend on the load, something like this. So both they can rotate. So we can have rotation at joint B, we can have rotation at joint C, or if we have lateral load, or unsymmetrical load even, we can have lateral deformation. So we can have theta B, we can have theta C, and we can have lateral deformation like delta. These independent deformation, we call it degree of freedom. In first step, in order to solve any structure with slope deflection method, we should be able to find degree of freedom. Later on you will see why it is important to find, but first step, we should be able to find degree of freedom for that system. The degree of freedom for that system means here the number of independent deformation we can have. Let's look at 2 different examples so you will understand how we can find it. Here, degree of freedom, it is 1. Only joint B can rotate. Here, for example, degree of freedom, it is here A, B, C. Joint A cannot rotate because we attach to the fixed support, so no rotation over there. Joint B can rotate, for example, deformation like this. So here we can have theta B, and joint C can rotate, so we have 2 degree freedom for this system. In order to find degree of freedom, look at to the joint first. All joint can rotate. If we attach to the fixed support, only cancel that. Any joint we attach to the fixed support, it cannot rotate because rotation is equal to 0. Other joint will add 1 degree of freedom. You see here, this can rotate. 1 rotation we can have here, another rotation here, so 2 degree freedom we have here. In order to find lateral deformation of the structure, convert all joint to the hinge, pure hinge. Then your structure will be unstable. The minimum number of members you can add to that system in order to make it stable. It will show you the number of independent lateral deformation. For example, this way. A, B, C, D. Let's find the degree of freedom for this system. First, each node can rotate except node A and D because we attach to the fixed support. So 1, 2, 1 here, another 1 here rotation we can have. 1 rotation at node B, another rotation at node C. So 2 degree of freedom for rotation we have. But this frame can deform laterally as well. In order to find that, convert all joint to the hinge like this. Now this system will be unstable. If you add load, it can collapse like this. In order to make it stable, if you add one member like this, one diagonal member, now this is stable because we have truss structure. It cannot move in horizontal direction. So we add only one member in order to make it stable. So one lateral deformation we can have in this frame and two rotation we can have, two node rotation we can have here. So degree of freedom totally will be 3 for this frame. Let's look at two other examples. For example, this frame. Let's look at the degree of freedom. Degree of freedom for this frame. How many nodes we have? 1, 2, 3, 4, 5. A, B, C, D, E. We have 5 nodes. Node A and E, they cannot rotate because using fixed support we attach to the ground, no rotation over there. But joint B or node B can rotate, node C can rotate, node D can rotate. So 3 rotational degree of freedom we have here. How many lateral deformation we can have? Convert this to the hinge, all of them, pure hinge. In your imagine all of them, they are pure hinge. Now this frame will fall down, it is unstable, it will collapse. In order to make it stable, if you add one member here, still it is not stable because you see this part is triangle like truss, it is stable, but again it can rotate this part respect to point A and this will collapse like this. So you need another member. If you add one more member like this, now this is triangle, this is another triangle, and this is another triangle. We have truss structure and it is stable. So how many members I added? 2 members. 2 lateral deflection we can have, 3 rotational degree freedom. So if we add together, degree of freedom for this frame will be 5. Let's look at to this frame. A, B, C, D. Again, we have 4 nodes, 2 of them they are fixed. So 2 rotational degree of freedom we have here. How about lateral one? If I convert all of them to the pure hinge, if I add one member only here, now this is stable. So totally degree of freedom for this frame will be 3. This is the way we will find degree of the freedom, because degree of freedom will give us how many equations do we need in order to solve this frame using the slope deflection method. Degree of freedom 3 means we have 3 unknowns. Degree of freedom 2, it means we have 2 unknowns. We will practice later more, only one snapshot. Briefly I explain what is the degree of freedom, but later on we will practice in several examples. Then we will need to figure out the slope deflection equation. First, let's look at the slope deflection assumption, because in order to use this method, in order to develop this method, we need to make some assumption. The slope deflection assumption I will summarize here. Assumptions in the slope deflection method. These are important assumptions. We should know with which assumption we end up with this equation. First assumption, the material of the structure is linear elastic. This is first assumption. You know, in most formula we have in mechanics of deformable body and structural analysis, at least in undergraduate level, we have to make this assumption, because all those formula, they are based on the Hooke's law. If our material it is not linear elastic, the material will not obey the Hooke's law. So the first assumption, in most cases we are making this assumption, the material of the structure is linear elastic. The second assumption is the structure is loaded within elastic limit. Means Hooke's law is valid. We are in small deformation range. This is important assumption. Axial displacement axial displacements, shear deformation, axial displacement, shear deformations are neglected. We don't consider the axial deformation if we use the slope deflection method. In reality, we have the axial deformation, but if we compare the axial deformation or shear deformation, in most cases, if we compare those with flexural or bending moment deformation, they are small, so we can neglect. But in some cases, we cannot neglect. But here, in order to find the slope deflection equation, we should make this assumption: axial displacement and shear deformations are neglected. Assumption number 4, only flexural deformations are considered. So deformation comes only from flexural deformation or bending moment. Let's look at one member to see how we can develop slope deflection equation. It is good to know slope deflection method is developed by in 1914. This method is developed by George A. Money. So since 1914-15 we use this method, and first this method is developed by George A. Money. He published a paper, and then this method, it was very popular for a while. After Hardy Cross developed moment distribution method, in most cases they use moment distribution method. But later on, because we have high-speed computer these days, and stiffness method will give us the capability to program. We can we can do a lot of programming, and if we want to use software or programming, direct stiffness method, it is much easier in order to develop those software. So using hand calculation, slope deflection method is very popular. Hardy Cross is very popular. But if you go to the programming area, direct stiffness method has a lot of applications, and most software you are using, like Risa 3D, SAP, ETABS, all of those, they use direct stiffness method in order to create that program. So let's look at today's slope deflection method. If we have one member, initially straight member, is subjected to, for example, one load like this. In general case, we will have bending deformation in this member. We will have, for example, rotation in both end A, B, and we will have bending moment here, MA, MB, and we will have lateral deflection like delta, and shear forces at the node like VA, VB. So the load will transfer here after deformation, and you remember initially was straight line, but then it will deform something like that. Using superposition, if the member length, for example, it is L and EI is constant, using superposition we can divide this to the different system, 4 different structures. One of them, if we have one straight beam subjected to that load, for example Q, what we will have, theta here is 0, theta here is 0, we will have fixed end moment here. I show with MB, for example A, this is joint B, this is joint A, fixed moment here, and fixed AB. I show this one with MB1, this one with MA1. So that external load will produce, if both end is fixed, no rotation, we neglect the rotation, we make it fixed, it will create fixed end moment only. Then these moments, if we have these moments one by one, if I apply here, for example, MA2, here I will have MB2. plus, if I have rotation here, for example, that rotation created by MB2, I will have reaction here, 1, 2, this should be 3, sorry, MB3, MA3, plus both sides, in general case, they can move respect to each other. So we can add another system, this one. MA4 and MB4, and this is lateral deflection delta. So if we add these four systems together, we will have the initial system in general case. We will have lateral deflection, we will have MB here, MA here, because we will have rotation at joint B, rotation at joint B like this, rotation at joint A like this, and end moment because of this external load. So these four systems summation using superposition will give us one member. In most general case, we have lateral deflection, we have external load, and we have rotation in both ends. So I can write MA is equal to MA1 plus MA2 plus MA3 plus MA4, and MB will be equal to MB1 plus MB2 plus MB3 plus MB4. So I divide this to the four different simple systems. If I add together using superposition, I can get initial structure. And if I calculate the moment for each one by one, and add together, I will get the total moment for this structural member. Let's do that one by one, see how we can find the slope deflection formula. First, MA and MA1, MB1 is end moment because of external load. When both ends they are fixed, we call it fixed end moment. We can find those using force method. For example, if we have beam, both end fixed, is subjected to concentrated load at middle, or we have beam subjected to distributed load, and it is uniform distributed load. The intensity is W. Here the support reaction, for example, PL over 8, PL over 8, or here support reaction will be W L squared over 12, W L squared over 12. We can find these one by one using force method or superposition, and we can develop a table. That table we have in most structural analysis book, textbook in the appendix side, or if you Google it, fixed end moment, for different loading scenario, you can find this fixed end moment. So MA1 and MB1, they are fixed end moment. I call it MA1, M fixed AB, I can find using table, and those tables, they develop it using force method or superposition, and we can develop that. That is easy, but because they already develop it, we will use those tables. This is M fixed, BA. It means fixed end moment because of external load. So this term we can find it. Let's look at two, MA2 and MB2. One of them I will find it, other MA2, MB2, one of them I will find it, then MA3 and B3, it is the same thing, because if you look at here, I call this MA2 and this one MA3. One of them, if I find, other one, it is the same thing. Let's find that one. See what is the relationship between moment and theta over there. If I have this beam, and I apply moment M here, this beam will deform something like this. So we will have theta here. If I call this in MA, this will be theta A. So what is the relationship between MA and theta A? I can find that. It is easy to find. First I should find this reaction R. How I can find that? Using superposition, that will be equal to, I will apply MA here, that I will have deflection here. Because of that deflection, we will have this reaction upward, that will deform to the upside, this is downside. Those deformation should be equal, because finally deflection here is equal to 0. If I add moment here, what will be this deflection? Using virtual work method, you can find that. It is easy to find using virtual work method. That will be, let's see, if I add M here, deflection, I want to find deflection, so I will apply unit load here. So the bending moment diagram, because of the moment, will be MA. Because of the unit load, it will be negative L. If I multiply together, coefficient of triangle to rectangle, it is 1 over 2M times L over EI. So it will be L squared over 2EI. This is deflection because of this bending moment. How about deflection because of the load? Deflection because of the load, it will be load L cubed over 3EI. Those deflections should be equal, so I will plug equal. If I plug those equal, I can find R. I can find R from here, because R L cubed over 3EI will be equal to M L squared over 2EI. From here, R will be 3M over 2L. So this will be 3M over 2L. If I find this reaction, let's see what will be the reaction moment here. The reaction moment here, if I apply, for example, M, what is the reaction moment here? The reaction moment here, this is, for example, point B, this is point A. And if I take moment respect to here, minus mb minus m plus r times L 3m over 2L times L is equal to 0. From here you will find MB will be equal to this, they will cancel each other, this will be 1.5 m minus m 0.5 m. If I take to other side, it will be m over 2 negative, let's see, I did mistake or not. So m negative m plus 3m over 2L times L is equal to 0. So if this is m, okay, minus mb minus m3m over L, L and L, they will cancel each other. From here, negative mb minus m minus, this will be 1.5 m is equal to 0. This is positive, so mb will be positive 0.5 m is equal to 0. If I take the other side, it will be negative, both negative, they will cancel each other. So mb here will be m over 2. From here we can understand, if I apply moment m here, the reaction here will be m over 2. Pay attention. If I have cantilever beam, if I apply moment m here, the reaction here, what's the reaction here? Once I'm applying the moment m here, the reaction here will be m. Why? Because this point for example BA, point A can move down to this point. So both reaction, they will be equal. One of them, it will be clockwise, another one, it will be counterclockwise. But if I don't allow to point A move down, I put support over there. In that case, everything is the same. This support will not allow point A move down. In that case, if I apply moment M, the reaction will be here, will be half of that, m over 2, and deformation shape like this, and both, you see, the moment will be in the same direction. If this is clockwise, this will be clockwise too. Now, if I draw moment diagram for this system, moment here m is negative because create compression underneath of the beam. Moment here is positive because it create tension underneath of the beam. So m over 2m. If I attach together, this is negative, this is positive, this will be 2L over 3, this will be L over 3. Now I want to find the slope at point A. So I will apply this time unit moment over there. So at point A, I will apply unit moment using virtual work method. So if I apply unit moment, this side will be 1, this side will be half 1 over 2. I will attach together, this is negative, this is positive, again 2L over 3, this will be L over 3. So if I want to find theta A, I should multiply this diagram to this diagram using virtual work method. Let's do that. If I multiply these together, theta A will be equal to triangle to triangle, the coefficient is 1 over 3 times L, triangle to triangle, the coefficient is 1 over 3 times M times 1 times 2L over 3 EI, the length for this part, plus triangle to triangle, coefficient 1 over 3, m over 2 times 1 over 2 times length L over 3 divided by EI. If I add these together, I will get, let's see, theta A will be, this will be 3 times 3, 9 times, let's see, everything is right or not. This will be 9, 27, 3, sorry, I made mistake, this belongs to here. So 3 times 3 will be 9, so it will be 2ml, 3 times 3, 9 EI, plus, let's look at here, 2 by 2 will be 4, 4 times 3 will be 12, 12 times 3 it will be 36, so it will be 36 EI ML. The answer for this, if I add this together, it will be 36 EI divided by 36, it will be ml, plus 4, that will be 8 ml. So finally, if I add these together, theta A will be equal to ml plus 8 ml, will be 9 ml over 36 EI. I can simplify this from here, 9 with 36. If I simplify that, theta A will be ml over 4 EI. From here, I can write m over theta, it is equal to 4 EI over L, or m will be equal to 4 EI over L theta. Yes. So, if I apply moment m here, I call it, for example, MA. We will have rotation here, I call that theta A. The relationship between MA and theta A will be this relationship. MA is equal to 4 EI over L theta A. I find that using virtual work method. It is easy procedure. You can do that one more time and you will see you will end up with the same result. So if here now MA is equal to 4 EI over L theta A, because this reaction will be half of that, MB, so here MB will be half of this, it will be 2 EI over L theta A. Remember this. Let's look at to see the final case. If we have two ends fixed and we have lateral deflection, what will happen? Both ends fixed, initially is like this, then after deformation will be like this, Here we will have deformation delta. The end moment, which I call it in superposition A4, MB4, if you remember, it is easy to find. If you look at to the deformed shape, it should be symmetrical. This is L initially. So at L over 2, you see the curvature direction will change at this point. I call it point O. The curvature direction at point O will change. Here the curvature, it is convex shape, so but here the curvature shape, it is concave shape. So from convex to the concave, the curvature direction is changing. At one point, curvature will be equal to the 0 because direction will change. Before this, it is convex. After that, it is concave. So at that point, curvature should be equal to 0. That point, usually in structural analysis, we call it inflection point. So we call it inflection point. Because of symmetry here, inflection point will be at L over 2. If this is delta and this is L over 2, the deformation here will be half of delta. Because of symmetry, this will be delta over 2, and that point O, we call it inflection point. If you want, I can define like this. Inflection point is a point I define like this. Inflection point, a point of curvature at which a change in the direction of curvature takes place. The inflection point, a point of curvature at which a change in the direction of curvature occurs or takes place. We call it inflection point. It means from that point, for example here, inflection point, that point curvature is equal to 0. Before that and after that, the curvature shape is different. The curvature direction is different. For example, here, in this case, before O, our curvature, it is convex shape. After that, it is concave shape. So at point O, from convex, it goes to the concave. So the curvature at point O should be equal to 0. We call it inflection point. Inflection point is a straight point. There is no curvature over there. There is no curvature over there means internal moment at that point should be equal to 0, because internal moment will create curvature. If you see the curvature is 0, it means internal moment is equal to 0. If internal moment is equal to 0, it means it behaves similar to the hinge. Now, if I look at to the half of this beam, it deforms like this. Here is hinge. So if I cut through this hinge, the deformation here, because of symmetry, if this is delta, this will be delta over 2. At cut point, the internal shear force, for example, if I call it P, how much is that P? I can find in terms of delta. This length, it is L over 2. P times the length L over 2 Q over 3 EI. it creates deflection delta over 2. From here I can find P. So from here I can write P is equal to 12 EI delta over L cube, because 2 times 2 will be 4 times 2, 8. So I can write here like this. Let's see. 2p L cube over 8 is equal to 3EI delta. This 2 and this 8, they can cancel. This will be 4. 4 times 3, it will be 12. P will be 12 EI delta over L cube. Now, that P will create moment at support. The moment at support will be that P here at inflection point times L over 2. So, moment here, M, will be P times L over 2, because P was 12 EI delta over L cube times L over 2, and will be equal to, from here, 6 EI delta over L square. And for the same reason, the M here in another support again will be 6 EI delta over L square. So I can write, if I have one beam, both support they are fixed, one support respect to another support moves as much as delta, moment here will be 6 EI delta over L square, moment here will be equal to 6 EI delta over L square. I find that. Now I add all these equations together, see what we will get. So if I add all these 4 cases, both end fixed moment, one end is fixed and one end is hinged, another end is hinged, another end is fixed, 2 end is fixed but they deform in lateral direction as much as delta. In that case, MA, moment at support A, they call it MAB as well, will be equal to MA1 plus MA2 plus MA3 plus MA4. From here, MAB will be equal to MA1, it is fixed end support reaction because of external load, as I explained, we can find from table, plus minus depends on your direction. You assume it is positive or negative. If I assume counterclockwise moment is positive and counterclockwise rotation is positive, clockwise will be negative. So I assume counterclockwise moment is positive, counterclockwise rotation is positive. So from here, for example, this will be positive because counterclockwise, this will be negative because it is clockwise. So here positive, I should write negative because it is clockwise, minus, if I add here MA2, what is the theta here? It is theta A. What is the relationship between MA2 and theta? theta A times 4EI over L will be MA2. So instead of that, I will put 4EI over L theta A. If I apply MB2, I remove that part if you remember. If I apply MB2, what will be the reaction here? The reaction here will be half of MB2 because this is theta B. This will be 4EI theta B over L. This will be 2EI, half of that, theta B over L. So if I add that, it will be again clockwise, negative 2EI over L theta B. This reaction, I find it is 6EI delta over L squared, and this is, you see, counterclockwise, so positive 6EI delta over L squared. This is for A side. For B side, you can make similar discussion. MBA, you can write M fixed BA minus 2EI over L theta A minus 4EI over L theta B plus 6EI over L squared delta. Finally, if I rewrite this and a little bit write in different form, make order better, I can write the slope deflection equation. MAB is equal to M fix AB plus 2EI over L times minus 2 theta A minus theta B plus 3 delta over L, because if we multiply this inside of parentheses, this will be negative 4EI over L theta A, negative 2EI over L theta B, this will be positive 6EI delta over L squared. In similar way, M BA will be equal to M fixed BA plus 2EI over L minus 2 theta B minus theta A plus 3 delta over L. These are slope deflection equations. Using these equations, we will able to solve indeterminate structure. We will able to find the reaction and deformation in indeterminate structure. Next session, I will solve you different example. You will see how we can apply this equation. Thank you so much for watching this lecture. See you next session. Bye bye.